Words in a sentence hold meaning, but their order matters. So to grasp this sequence information, natural language processing models use positional embeddings. So today we will understand what positional embeddings are. Now this positional embedding is a technique used in transformer-based model networks which helps the model understand the relative position of words within a sentence. And it is similar to how musicians use sheet music to understand the position of notes within a melody. Imagine a sentence like, "The quick brown fox jumps over the lazy dog." Here, each word in a sentence has a specific position. Now, this positional embedding are used to encode this positional information into the word embeddings, allowing the transformer model to learn from the order of words in the sentence. So to illustrate this, think of it as adding numbers to represent position after the word embedding. For example, the first word "the" would have additional number 1 added to its embedding. The second word "quick" would have 2 and so on. So this way the model can understand that "quick" comes after "the" in the sentence. And this positional information is crucial for understanding the meaning of sentence. So by learning from positional embeddings, the transformer model can better distinguish between similar words used in different contexts, like jump in jumps over and jumped in jumped over. So let's understand it better using a Python code. So here it's a simple example of how to implement positional embeddings in Python using NumPy. In this example, we'll create a sign-based positional embedding, which is a common technique used in transformer-based model in BERT. So let's understand this. First line says import numpy's NP. Well, this line imports the NumPy library, which is a fundamental package for numerical computing in Python. Now, the second line defines a function name, create sinusoidal positional embeddings, and it takes a single input parameter, maximum length, which determines the number of rows in the positional embedding matrix. Now, this third line creates a one-dimensional array of integer from 0 to maximum length -1. It then reshapes the array into a two-dimensional matrix with a maximum length row and one column. And this matrix will be used to create the positional embeddings. Now next, we define the embedding size, which determines the number of columns in the final positional embedding matrix. In practice, you would choose an embedding size appropriate for your model. And now next line, now this line duplicates the positional indice matrix along the column to create a matrix with embedding size by 2 columns. And this is necessary because we are creating a matrix of cosine and sine values for each position. Now comes this div term. Now this line calculates a divisor for the sine and cosine values, and this sign, this division sign operator, basically it performs integer division, which is necessary to create a frequency spectrum for the sinusoidal embeddings. Now next line creates a matrix of sine values based on the positional embedding and this division term, and the sine values are assigned to every other column 0, 2, 4, etc. of this positional embedding matrix. Now next, it creates a matrix of cosine values based on this positional embedding and this div term, and here the cosine values are assigned to other columns like 1, 3, 5 of this positional embedding matrix. Now optionally you can normalize the embeddings, and finally you return the positional embedding. So this line will return the positional embedding matrix, which now contains the sinusoidal positional embedding for each position. Now next, we will take the maximum length to 100, which is used as an example. In practice, you would choose the appropriate maximum length based on your used case. And then we call the create sinusoidal positional embedding function with the max length parameter and assign the resulting positional embeddings to the positional embedding variables. And finally, we print the positional embedding matrix, which display the generated sinusoidal positional embeddings. Thank you.